Okay, so one more useful application of the above formalism is purification. Uh, what do I mean by it? Let's say you are given a system rho A. This need not be a pure state. Now, by purification, I mean that it is possible to introduce another system R and define a pure state on the larger system such that rho A is given by the partial tracing out R of this guy, which was the density matrix obtained from the pure state AR. So this mathematical construction is called purification. So I'm going to a larger Hilbert space and converting the original density matrix into a pure state whose reduction or partial trace back gives me the original density matrix. So R is called as the reference system. You can also regard R as just a mathematical construct or a fictitious system. And so what's the proof? So let me have the spectral decomposition of A, rows of A. I'm going to use the subscript or the upper script interchangeably, doesn't really matter. So let me just call it as rows of A over here. So this is the spectral decomposition of the density matrix. And let me consider a pure state. Consider a pure state AR given by these guys. Sum over I. Notice these lambdas are the same as these lambdas, and this is the basis, and I have introduced another system here and its orthonormal basis. So what does it give me? It gives me the density matrix looks like this guy, and taking partial trace this gives us so this is the partial trace tracing out the uh, system R. Convince yourself that's going to give you a Kronecker delta function with these guys, which reduces to nothing but which was nothing but rho A. So that's why we say that the state AR, which is a pure state, is a purification of rho A. So this is a very useful construct in quantum information theory. You go to a higher Hilbert space or a larger Hilbert space, include another fictitious mathematical construct system R, and extend any mixed state into a pure state. And the mixed state is recovered back by taking the partial trace. So, of course, there's also note that this has a close relationship with the Schmidt decomposition. So, note the close relationship with Schmidt decomposition. How so? Well, the process to purify a mixed state of system A is to define a pure state, you know. So rho A to purification, I define a state, a pure state AR, whose Schmidt basis for system A was just the basis obtained via spectral decomposition of A uh, for system A was just the basis obtained via spectral decomposition of A, and the Schmidt coefficients are what are they? Schmidt coefficients, remember, were square root of lambda, are square root of eigenvalues of rho A. So that gives us a recipe uh, to construct a purification of any mixed state. So purification and Schmidt decomposition are intimately related concepts, very, very useful in quantum information theory.